execution buffer is. The reason it's 22 bytes is I wanted it to round up to a nice round number like 100 bytes. Right? It could be smaller than that, and the attack would be a little quicker, but the worm would run slower. It could be bigger than that, and the worm would run a little faster. So what we need is a MicroVM that will take chunks of code from the worm, copy them into this location, let them run, and then get the next chunk from the worm. So that's what the MicroVM does. We have the worm IP address, or the worm instruction pointer, which we initialize to 0, which is the beginning of the worm. Then we copy the worm code into the buffer, and we update the worm IP to point to the next block of the worm. So before we start executing the worm code, we're setting the instruction pointer to point to what should execute next. And then we copy, we save the MicroVM registers, so when we get back to the MicroVM, it's going to execute correctly. We load the worm registers that we saved. We fall through, right? We don't even need to jump. We fall through the worm code. We run that. Then we save the worm registers, restore the MicroVM registers, and jump back to start reading the next block. Okay, so we only need to break enough keys for that. We need all this other data around, but we don't need to break keys to put it there. We just need space for it. Yes?
Well, sometimes the worm code may call the system code. Or your MicroVM take care of the system code.
Okay, good point. So if we want to do jumps, we got a problem here, right? If we do a jump and we try to jump to an arbitrary address, it's going to be somewhere that we don't know the instruction key. So we need to do something special to make jumps. System calls themselves are actually easier than jumps. System calls we can do normally because they just use registers and they return back to where you were. To make jumps, though, is tough. And we're going to need to make jumps. So within a block, we can do a short relative jump very easily. But if the execution buffer is only 22 bytes, that's not going to be good enough. That we're going to need to have loops that are longer than 22 bytes. And 22 bytes is only enough for 4 or 5 instructions. So if you want to make a jump between blocks, well, we need some way of having that happen within the MicroVM. If we constrain it to only have jumps from the end of the block to the beginning of the block, we can do it pretty easily. So the way to do a jump is to change the worm IP. Right? That's the instruction pointer for the worm. So to do a jump, we just need to change the value of the worm IP. That value is stored on the stack. Right? Remember the MicroVM, before it starts executing the worm code, it updates the worm IP to point to the next block and puts that on the stack. So that means in order to do a jump within the worm code, what we need to do is change the worm IP value, which is stored on the stack. If we want to execute a conditional jump in the worm code, what we do is instead of executing that jump, we use the opposite condition. And for every conditional jump, there's one with its opposite. And we use the opposite condition to jump over the next instruction. And because this has to be at the end of the block, that means we're jumping back into the MicroVM. And so if the jump's not taken, we take the opposite jump, and the worm code will continue to the next block. If it is taken, we execute this move instruction, which stores the target address in the location on the stack that stores the worm IP. So when we go back to the MicroVM code, when it tries to read the next block of the worm, it's going to read the one from the target instead of the next block. Okay, so that means we can execute any worm we want with this 100 byte of key that we've acquired. So all we need to do to deploy a worm is learn 100 bytes of key. And we can do that really quickly. Right? That takes, on the experiments we've done, the median time that takes is 311 seconds. So just over 5 minutes, and only a bit over 8,000 attempts. And then we can inject into the compromised machine. We put the MicroVM code encrypted with those key bytes. We inject the worm code pre-encrypted. So we know where the worm code is going to run because we know where the worm execution buffer is, and we know the key bytes there. So as part of the deployment, we pre-encrypt all the bytes of the worm to have the right key for the location where they'll run. We need to be a little careful because we can't inject nulls. So if the bytes that we want to inject would be a null, we need to insert a no-op. And we can do that. And if we're lucky, we can inject the whole MicroVM almost all the time within 100 bytes If we need more no-ops, we might need an extra byte or two. And then as we propagate the worm, we need to keep track of the key bytes, because when we find the next machine to attack, we're going to learn the key bytes on that machine. To send the worm to it, we need to XOR out the keys on this machine, because it was pre-encrypted with those, and XOR in the keys on the new machine. OK, yes?
So an attempt, 8,400 attempts. So a crash is, the number of crashes is going to be of the same order of magnitude.
We're going to need to crash about, 8,400 times. That's a lot, but processes crash pretty frequently without getting noticed by system admins. So if your system admin is really paying attention, they might notice before the worm succeeds. But given it's only happening within 5 minutes, so unless they have something automatic to shut down their network or to shut down their machine when they've seen a certain number of crashes, they probably still don't have time to react to it.
And just a quick clarification question. Of the 256 possibilities in a byte, how many are legitimate instructions in this architecture? I mean, what causes a crash? Is it that it is not an instruction?
So almost the instruction set is very dense. So almost everything could be a legal instruction, but given the state of the processor, it's often not. Okay. And in our experience, we find about a little less than half the time is a random guess harmless. So more than half the time, random bits will cause the process to crash. So if it's an instruction that, say, reads memory, that could be valid depending on the memory segment of the process you're running it in. Most of the time, it's going to cause a crash. Other questions now? OK, so if we want to prevent this attack, well, we can think about all the things that were necessary for it to succeed and try to change them. So the first thing was to have a vulnerability. And so that's easy to fix. We should just eliminate all the vulnerabilities, and we don't have that problem. And if we can just convince everyone who writes code to rewrite all their code in a type-safe language, we won't have almost all the kinds of vulnerabilities we care about. Unfortunately, efforts to do that have not yet been very successful. So there are other things that we can prevent, even if we use to prevent this attack, even if the server still has vulnerabilities. One thing it relied on was being able to make repeated guesses with the same key. So if we made sure that every time a process crashes, we re-randomize the program, then this attack wouldn't work. You couldn't incrementally guess the key. This would enable a denial of service attack if it takes a lot of processing to re-randomize the program. We could try to make it harder to observe when the process under attack crashes. This is a little tricky to do, but maybe if we modify the kernel, we could make it so a socket stays open even when the server crashes, at least for some amount of time. The most obvious thing we could do is make it harder to cryptanalyze the results. Right? Instead of just using XOR as the encryption technique, use some strong cipher like AES. There's a big drawback to this, though. It takes a lot of time to do that encryption. So if you need to do this encryption while a process is running, which you need to, that may slow down your server enough that it's not feasible. So those are sort of specific defenses against this specific attack. I think what's probably more worth thinking about is, are there more general defenses? So in general, what this attack relied on was being able to break a secret. So if you want things to be more secure, a better solution is to find some way to avoid secrets. Right? It's hard to keep secrets. We've shown one way a remote attacker can learn a secret from a server based on observing its results. There are lots of other ways if you rely on secrets that it could be broken. Maybe a remote attacker can read locations in memory and find the key. Maybe they know an insider who can tell them what the key is. So what we'd like is some way of, instead of relying on keeping a secret for security, having security that doesn't rely on any secrets. And if we have this, maybe we can get to the point where we can actually prove properties